Hi, welcome back to General Chemistry 1. I'm Dr. Fang Xu. We talk about solutions and displacement reactions, and in this video, we're going to talk about ionic equations. So what is an ionic equation? An ionic equation is a chemical equation in which the electrolytes in an aqueous solution are expressed as dissociated ions. For example, we take we take the same example used before as precipitation reaction. If we write out all the compounds, the chemical formulas of reactants and products, we can get a molecular equation. So showing us here. A molecular equation shows the chemical formulas. It does not show the dissociation of chemicals in water. As you can see here, the silver nitrate is written as silver AgNO3, and then sodium chromate is Na2CrO4. Like everything is stayed together as a chemical. It does not show its dissociation in water. If we want to indicate in the water solution, what are the ions presented in the water solution? We can write the total ionic equation. A total ionic equation shows all possible dissociated ions in a solution. For example, here, because sodium nitrate and because silver nitrate and sodium chromate are both fully soluble compound, we split them apart into cations and anions. Okay, we have silver cations, nitrate anions, sodium cations, and chromate anions. But for the product, because silver chromate is an insoluble compound, so we keep it together as the chemical formula. It does not, approximately it does not dissociate in the water. For the other product, sodium nitrate, it can also be split into sodium ions and nitrate anions. This is the total ionic equation, shows all possible dissociated ions in solution. However, if you take a close look at it, we have 2 sodium ions in the reactant and 2 sodium ions in the product. These 2 can actually cancel out. So if we cancel out all same species before and after reaction, we can get the net ionic equation. It only shows the species that are involved in the reaction in a solution. So if we clean up the total ionic equation, what we really get is 2 silver cations react with 1 chromate anions to get the precipitated product, silver chromate. So ionic equation reflects the true chemical reactions that occurs in the solution. In this course, General Chemistry 1, we also expect you to be able to write net ionic equation. Let's take a look at another example. For example, here is an acid-base reaction. You should all be familiar in writing the molecular equation because that's the chemical equation we've been talking about in previous lectures and the videos. Okay, so also you should balance this equation first. Yeah, so from the molecular equation, we can first write the total ionic equation, split apart each chemicals that are soluble in water. If the chemical is not soluble in water, then we don't split them apart. So for this one, hydrochloric acid can be written as hydrogen plus and Cl minus. Okay, sodium hydroxide can be split as sodium ion and hydroxide anion. The same with salt, sodium chloride. In the product side, we can split that as sodium cation and chloride anion. The water, we don't split it apart. It's in the water solution, so we assume water does not dissociate completely. So for the total ionic equation, we write it out as it is. But pay attention, we don't split water, we don't split insoluble species, we don't split weak electrolyte or non-electrolyte. Okay, anything that is not 100% fully dissociated in water, we don't split them. From the total ionic equation, I just write it out again, we can cancel out the same species before and after reaction. For example, here, chloride anions, it's the same before and after, we can cancel that out. And also sodium cations, we can cancel that out. So these ions that can be canceled out are called spectator ions. These are the ions that are present in a solution but don't take part in a solution's chemical reaction. Okay, so after we clear out these spectator ions, we can see what exactly took part in the reaction. For this acid-base reaction, it's the hydrogen plus hydroxide that forms water. So this is the net ionic equation. And also from this net ionic equation, we can see the true, or we can see the fundamental underlying origin of the acid-base reaction is that proton, the hydrogen plus, transfer from acid to base and then create water. Okay, there are a few notes for writing an ionic equation. First, as I said before, don't split water insoluble species, weak electrolytes, or non-electrolytes in an ionic equation. For example, acetic acid, it's a weak acid. So when we write an ionic equation for acetic acid reacting with a strong base, we keep acetic acid as it is in the chemical formula, CH3COOH. We don't split it apart. Also, you need to write the final product for unstable species, such as carbonic acid, sulfurous acid, and ammonium. For carbonic acid, it's unstable and can produce water and carbon dioxide. For sulfuric acid, it's also unstable, can produce water and sulfur dioxide. For ammonium, it's not a base by itself, but it can react with water and form the ammonium hydroxide, which is actually a weak base. Let's take an example. Say if we have if we have hydrofluoric acid reacting with potassium carbonate. Originally, if you just do the displacement reactions and form the weak sulfuric acid, it further decomposes, and you should write the product as water and CO2. All right, let's take a look at the problem that's writing ionic equations. Write balance the total and net ionic equations for the reaction between aqueous solutions of calcium hydrogen carbonate and hydrobromic acid. Use a curved arrow in the net ionic equation to show the proton transfer. Give the name and formula of the salt that is present when the water evaporates. Okay, so for writing ionic equations, we first write molecular equations. The calcium hydrogen carbonate react with hydrobromic acid. Because you do the displacement reaction, exchange the anions, and we can find the salt and also another weak acid here. So it's a strong acid in the reactant and a weak acid in the product. Because of the carbonic is a weak acid and is not stable, it further decomposes to CO2 and water. We should write the molecular equation as it is. Okay, use CO2 and water as the product. Because we have a 2 as a coefficient in front of our carbonic acid, so when we displace or replace the carbonic acid with CO2 and water, each CO2 and each water should have a coefficient of 2 also. From this molecular equation, we can write the total ionic equation. Okay, pay attention to the stoichiometry here. For each calcium hydrogen carbonate, because of the charge neutral, we need to have 2 hydrogen carbonate to match 1 calcium. So when you dissociate that or split that into ions, we should put 2 as a coefficient before hydrogen carbonate. Okay, so the same thing as bromide anion. We have 2 in the coefficient, so every splitted ions in the compound should multiply the coefficient. Okay, so for here, bromide anions, we should also put the 2 in front of it. All right, the same thing. And for the same thing for the salt. For CO2 is a gas, so we don't see CO2 dissociate or split in the water, so we keep it as it is, and also the water. Okay, from the total ionic equation, we can clear the spectator or cancel out the spectator ions before and after reaction. In this case, it's calcium cation and bromide anions. So when you cancel out the bromide anions, it has to be the same, have the same coefficient. If, say, I'm just imagine before the reaction, if we have 3 bromide anions and after reaction we have 2 bromide anions, after we cancel out the spectator ions, we should have 1 leftover bromide anions as a reactant. Okay, so now clear the total ionic equation, we can get the net ionic equation. And that is 2 hydrogen carbonate react with 2 hydrogen to produce 2 CO2 and 2 water. Okay, all the coefficient are 2. So we can make the coefficient the smallest whole number by dividing or multiply the same common factor. So in this case, we divide every coefficient by 2, make it 1, 1, 1, 1. So now this is the net ionic equation. 1 hydrogen carbonate react with 1 proton to produce 1 CO2 in gas phase and 1 water in liquid phase. So if we want to use a curved arrow to show the proton transfer, it's from the acid to the base. And imagine if we evaporate all the solvent, what left over, going back to the molecular equation, what left over is a salt. So this is the calcium bromide. All right. The ionic equation can also be treated as a type of chemical equation. So we can also use ionic equation to complete a stoichiometry calculation. Since we talked about stoichiometry calculation before, I'm not going to give an example in this lecture. All right, this is the end of this video and see you next time.